is concerned, I don't have those, right? So Dr. F has those, so I think you may have to wait until he comes back, because I don't even know where they are. But you will be able to see them before your final. All right, so let's go ahead and talk about properties of parallelograms, chapter 5. This was actually in the curriculum to be done before the end of last semester, but things are a little different with the block days, so there's not as many class meetings. So things are going a little slower, which is good because that's more think-sync time for you guys. But this chapter is all about parallelograms. There's lots of theorems, lots of properties to help you prove things with parallelograms. So let's just think back, or y'all think back, to when you did quadrilaterals. So the definition of a quadrilateral, well, if you look at the prefix quad, that's kind of prompting you that it has how many sides? 4. So a quadrilateral is a polygon with 4 sides. And then the sum, if I add up all of the interior angles of a quadrilateral, it's 360 degrees. So if anything's missing, you can use that information to be able to find any missing angles. Now, here is the definition of a parallelogram. So definition. A parallelogram is a quadrilateral with both pairs of opposite sides parallel. So this is a definition of a parallelogram. And so let's go ahead and interpret this and make sure that we understand what this means. It's saying both pairs, and I'm a very visual person. So that's why I like to see things, because memorizing theorems and doing proofs that way, it gets a little messy. But if you can draw it and you can see it, I think for me, at least, it's easier. If you don't like it, well, oh, sorry, but that's how I see it. So a parallelogram is a quadrilateral with both sides parallel. So let's first go ahead and look at those both sides. Here is a side, and there's the other in its pair. So that is telling me that PQ is parallel to SR. And then since we said both sides are parallel, let's look at the other set, the other pair. And these, again, and I don't know what you know and what you don't know as far as notation and language, so stop me if I say something or if I'm being redundant, I apologize. So this is showing that these two are parallel. This is showing that these two are parallel. So then I also have QR is parallel to PS. That's what this is saying. So now this is the shape we're working with, and this is the shape that I gave you, okay? So if I'm looking at this, we can prove the upcoming theorems in a classical approach, meaning the 2-column proofs, but you can also use a transformational approach using patty paper and doing rotations to show what the theorems are saying. So let's go ahead and look at the first theorem. I'm going to go ahead and give it a name. You don't really, I don't think y'all need to know the names. I think you just need to explain what the theorem is saying in your 2-column proofs. But I'm going to go ahead and give it a name just so we can remember them maybe. Like if you write a summary sheet of the things that you've learned and you want to list all the theorems, you write the names and then maybe that would prompt you to what the theorem says. So this theorem, which I'm going to call, or it is also known as, the parallelogram opposite sides theorem. Okay. And what this theorem tells you is, well, opposite sides. We're working at opposite sides. The opposite sides of a parallelogram are congruent. Now, by definition, we knew they were parallel. But there's a theorem that says these same opposite sides are in fact congruent. So I'm going to rewrite this as in an if-then form. So if quadrilateral is a parallelogram, then the opposite sides are congruent. So that's what the theorem says. Now, how do we denote that the opposite sides are congruent? We have these little tick marks. So again, we're saying that these two are congruent, have the same length. These two pairs are congruent and have the same length. Now, I like to visually see this before I prove it, just to, you know, I want to see it to believe it. So I gave you a little parallelogram. And I'm going to go ahead and take my patty paper, and it's easier to write on the side that's not shiny, if you can even tell that, and a pencil works well. So I'm going to go ahead and draw, let me get a regular pencil, on the patty paper. So there's A, I'm just tracing it, A, B, C, D. And that's my parallelogram to begin with. Now, what this point E is, well, if I go ahead and take this and make the diagonals. So if I want these diagonals here, how am I going to do that? I'm going to fold my little patty paper through C and A. And again, this isn't going to be absolutely perfect, but it's to the best of our ability. So do you see this little diagonal here? Okay. And these are all going to be pieces that we need. Then I'm going to take BD and I'm going to fold it again, passing through B and D. And I have my other diagonal. And where these two diagonals intersect is this point E. And that's what we're going to rotate about to visualize these. So if I take this, this is saying that the opposite sides of a parallelogram are congruent. Okay, so if I place this back on top and I put my pencil at E and I rotate the top patty paper 180 degrees, I'm going to show what? That this is the same length as this. This is the same length as this. And that's abundantly clear because if I rotate it 180 degrees, whoop, there they are. Right? So this is showing that AB is congruent to CD and our original DC is congruent to AB. And similarly that these two are congruent. Do you see that? Isn't that nice? That's not, I like it. Okay, so again, we just pin it at E and we can take bits and pieces and we'll do the same thing with the angles and we'll be able to see that the angles are congruent in another theorem. Okay? So let's go ahead and see, that was a geometric transformational approach to the theorem. Let's go ahead and do a proof using the classical approach. So the classical approach is the two-column proof. And you're very fortunate because they actually give you how many lines that you're supposed to be using to give you a hint. Now, this is actually the only proof of a theorem that we're going to do in this class today. But, you know, you can prove all these theorems, of course. So let's go ahead and see what we've been given. Well, we've been given a parallelogram. And I've already told you it's a parallelogram by denoting the opposite sides are parallel. So I have parallelogram P, Q, R, and S. Now, I can write out the word parallelogram or I can denote it with the symbol. Just make sure your symbols kind of do look like parallelograms, right? Don't just draw a little rectangle. Okay, so you are given a parallelogram. What we want to prove is that, well, opposite sides are congruent. So I need to prove that PQ is congruent to SR. So PQ is congruent to SR. I also, since it says in the theorem that both sides, we have to prove also and QR is congruent to what? PS. All right, so I start with the given. So I have a parallelogram that has been given, PQRS, that is given. And the first thing I want to do is I want to, I want to draw the line segment PR. Now, we know by definition that through any 2 points, I can draw what? Exactly one line. And in this case, exactly one line segment, right? Because I'm drawing PR. So let's go ahead and draw PR. Okay. Now, I'm going to use the definition of a parallelogram, And what does the definition tell us? It tells us that the sides are parallel. So then if I have this, I can state that the opposite sides are parallel. So in other words, PQ is parallel to SR and QR is parallel to PS. Now, what have we created? By drawing that diagonal, what have we created? What do you see here? I have two triangles, okay? If I have two triangles, what do we normally do? Or what have you done in the past when you're given two triangles? What do you try to show? That they're congruent, because once we have congruency of triangles, what do we know about their corresponding parts? That they're congruent, right? So when we can create triangles, let's do it. So in this case, I can now say that QPR, this triangle, is congruent to SRP. Let's write that out. Right? Okay. Well, let's actually talk about the angles, right? Because these are we have angles, right? So I have angle QPR is congruent to angle SRP. Let's denote those angles. QPR. So this angle is going to be congruent. Oops, I didn't write I said something, but I didn't write it. SRP. And how do I know that? Alternate interior angles are congruent. So I have parallel lines cut by a transversal. So alternate interior angles are going to be congruent. So the fact that we have parallel lines implies that alternate interior angles are congruent. Do I have another set of angles that are congruent? What? Beautiful. So let's state those as well using the same information. I have angle RPS is congruent to angle QRP. Same reason, right? And that's parallel lines. Now, we created this PR, so let's go ahead and utilize this PR. Let's say something about PR. Let's say that PR is congruent to PR. How do we know that's, what justification would we use to state that? Reflexive. And look what we now have. We know that these are congruent. Well, we're getting to that these are congruent, but what do we have? Angle, side, angle. That's right. So by angle, side, angle, I know that triangle PQR is congruent to triangle RSP. And if we can prove that the triangle is incongruent, then we can prove that the corresponding sides, the opposite sides of those congruent triangles, are also congruent. So by CPCTC, I have PQ is congruent to SR, and I have QR is congruent to PS. And that is exactly what we were supposed to prove. Right? Any questions on that? No? Okay. Let's talk about another theorem, because there's oh so many theorems, lots of theorems. Okay, I like to call this one, it's also known as the parallelogram opposite angles theorem. So I'm talking about opposite angles now. And what this theorem states is that the opposite angles of a parallelogram are congruent. I can go back to my triangle and I can show that this angle BCD is congruent to this angle. Again, just by rotating it 180 degrees, I can see that they're congruent. Yeah, same thing is true for these two. I can shade them and then rotate them, rotating 180 degrees. So if the quadrilateral is a parallelogram, the opposite angles are congruent. So this is congruent to this, denoted by those tick marks, and this is congruent to this. So if we use this information, now these are great little puzzles. I just love these because there's so much stuff that you know, and so you can just use little deductive reasoning to like figure out the missing pieces. So again, I have a parallelogram. I need to find X, Y, and Z. So we're going to find all the measurements. Now, keeping in mind that the two sides are parallel and congruent. Parallel and congruent. So there's some things that I already know. What is the first thing that you can, which one would you like to find first? Y, okay, so what is Y?
65.
Y is 65, exactly, because we know that the opposite angles are congruent. So I already know that Y is 65 degrees because of the above theorem. Okay, what else would you like to find? What would you like to find next? X, you want to find X? Okay, now how on earth are we going to find X? That's right. I'm going to take this 3x minus 2, which is the length of this line segment, and I'm going to set it equal to 25 since I know those two line segments are congruent. So let's go ahead and do that. I have 3x minus 2 equals 25. So I'm isolating the x. So I'm going to add 2 to both sides, giving me 3x equals what? And then what am I going to do? Divide each side by 3, so x equals 9. And I could substitute back in and check, right? And I'll get 25. Now, the last thing I have to find in this one is what on earth is Z? Ooh, there is a theorem that says that. Absolutely. So there's a couple of different ways you could do this one. You could use the fact that the sum of all of them equal 360. So I could say 65 plus Z plus another Z equal plus 65 equals 360. Or you could use the fact that, and that leads us to the next one, consecutive angles are supplementary, meaning they add up to be 180. So you can do it either way. It's completely up to you how you want to do that. So I don't care. I mean, whatever you want. You can say, if you use supplementary, you can say 180 degrees, or actually, yeah, 180 degrees minus, and we know this is 65 now, minus 65 is going to give me Z. So Z equals, Or you could do it the other way, the sum of all four, so 65 plus Z plus 65 plus another Z equals 360. You're going to get the same answer. It doesn't matter. Okay, you're frowning. Why are you frowning? We're good? Okay, we're good? Okay. Everybody online good? Speak up if you're not. Yeah. So this leads us to the next beautiful theorem, in my opinion. So this theorem, which is often referred to as the parallelogram consecutive angles theorem. Consecutive angles. What are consecutive angles? Well, consecutive angles, if I'm starting here and I'm traveling along the perimeter, consecutive angles would be 2 in a row. So this one plus this one is 180. If I start at F and go clockwise, 120 plus 60 is 180. 60 plus 120, these are all gonna, like 2 in a row, if I'm traveling, are gonna give me 180. And we can verify that, right? Angle F plus angle I is 60. Angle I plus angle H is 180. Angle H plus angle G is 180, and so on, right? Does that make sense? Okay. So let's look at an example. Here I have parallelogram J, L, K, M, and I need to find the measurements of all of these angles. Which one would you like to find first? There's one that I think is easier.
The alternate interior angle.
Okay, which means I'm looking for measure of angle
J.
Well, it doesn't matter which one. You want to do MJK?
Yeah.
Okay, so you want to do this one. These are parallel cut by a transversal, so it equals 75 degrees. And it doesn't matter what order you go. As long as you get all the values, it doesn't matter. Some people see things differently. It's okay. What else do we know? What using this theorem? Angle L. What is the measurement of angle L? Okay, because of this theorem up here that says the opposite angles of the parallelogram are congruent. So this we said was 75 degrees. This is 60 degrees. So angle L is 60 degrees. How are we going to find something else? MKJ. How are you going to, so you want to find this angle here. Okay, how are you finding this angle? Oh, yeah, that's right. It's part of a triangle. It's the third angle, interior angle of a triangle. And we know the sum of the interior angles adds up to be 180 degrees. So I can sit there and say, to find this, 180 minus 60 minus 75 equals what? 45 degrees. Beautiful. And then last but not least, I'm looking for K, J, L. And what degree measure is that going to be? And alternate interior angles, or you could have done the same thing. There's actually another way we could have done it, right? We know the sum of these two plus this is 180. So, yes, ma'am.
On a test, would it be wrong if you wrote parallelogram consecutive angles theorem? Do you write the name? Or do you want to write the consecutive angles of parallelogram?
Now that's personal preference. I'm gonna have to, I don't know what have you been naming them or have you been explaining them?
Yes, but like, if I wrote one of them, would they both be counted then?
I
count it wrong.
personally would count it right, but I need to check with everybody else on the team to see if it's okay. I personally would mark it right because you know which theorem it is, right? I don't know. I say yes, but then I don't want to.
Well, Dr. told us in the last semester that like some of them have like distinct names and others don't to describe what's going on.
Okay. This one they technically didn't give names to. I'm giving you the names that are being used, so you may want to describe them. But I mean, it's kind of one and the same, right?
Yeah. Okay.
I mean, like hypotenuse wave, the HL theorem. Have y'all done the HL theorem? Yeah, things like that. It's ASA. These. Maybe just describe them.
Okay.
I'm going to be to let you know. I'm going to be a little bit more lenient because I'm going to err on the side of giving you the benefit, not knowing how things have been done. So just don't put random words. I mean, it has to be legitimate, right? Okay, here we have another one. Woo! I have parallelogram PQRS. So I could have, given it to you like this. PQRS. I want to find X and I want to find Q. So how I'm going to look at this information to find X. I'm going to look at, and then I need to find Q. Anybody have any ideas how I'm going to do this? Beautiful. Using consecutive angles. Yeah. Good. Okay, so then I'm going to subtract 120 from each side. 3x equals what? Okay, so x equals 20. So I found something, which makes this angle what? What is 60 degrees, right? Because I just substitute the value in for x and I get the degree measure of the angle. Oh, golly, then that makes finding Q very easy. What is the measure of angle Q? And how do we know that? Yes, very good. Excellent. Not bad, right? These aren't bad. Okay, moving on. Another example. I just love these. Okay, I have a parallelogram. I have parallelogram ABCD. I have some angle measures. I know the measure of angle 1 equals 5x, so I'm just going to write that here. The measure of angle 2 is 3x. And then the measure of angle 3, x squared minus 24. I need to find what x is. Well, does anybody have any ideas how to start? Do I know a relationship? Do I know any two sets of angles that are congruent? Angle 1 and angle 3 are congruent, right? So the measure of angle 1 is congruent to the measure of angle 3. So that's saying that 5x equals x squared minus 24. Think back to algebra 1. Perhaps we want to put everything on one side of the equation, set it equal to 0. So it doesn't matter whether you move everything to the left-hand side of the equation by doing opposite operations or move it to the right. I personally want to keep x squared positive, so I'm going to subtract 5x from each side. That is going to give me x squared minus 5x minus 24 equals 0. Does everybody see this? How I went from here to here? Because I can change the sides because the two sides of the equation are balanced, right? So I can just put it on the left-hand side. And then I put this in exponentially descending order, x squared minus 5x minus 24. Because that's a beautiful little quadratic trinomial. And in your gut, that you should be just dying to do what to that quadratic trinomial to solve it?
Does it matter what order you put it in?
Order doesn't matter, but just to get you ready for algebra 2, you do want to put it in exponentially descending order, x squared, x to the first, x to the 0 power, because there's going to be a lot of factoring going on next year. So best practice is to put it in this form. Does it matter? No, but I would get in habit. Do we know how to factor this? It's the reverse operation of foiling it. Once you get the two factors, the two binomials, you foil them to check that you get this. So I'm looking for two binomials that when I do foil it, I get this. So do we know which the first term, what the first term in each of those binomials is? X, because they have to multiply to give you this. Now, the numbers that you choose to put here have to multiply to give you negative 24, but also have to add to give you negative 5. Okay, so now I've seen people do this. I don't really do this, but you know, if it helps you, by all means, they make that little eye chart and they say I have to multiply to get negative 24. So I multiply to get negative 24, and I'm choosing two numbers that sum. You've seen that symbol, sum, to give you negative 5. So let's think about that. Well, let's go ahead and write some factors. You're saying it's negative 8 and positive 3. Multiply, give me this, add to give me this. So that is correct. You may not see it the first time around, and there's going to be lots of other rules for factoring in the future. But that one is correct. We have to check that they multiply to give us this number, but add to give us this number. Now you said minus 8 and positive 3. Does the order matter in which you write these? Could have I written x plus 3 and x minus 8? Absolutely. Absolutely. The commutative property of multiplication says it doesn't matter. Now, at this point, there's a property that says when I have two things multiplied by each other, rather, set equal to 0, I can set each of them equal to 0. Zero product property. So I can set each of these little binomials equal to 0 and solve for x. So in this case, I get x equal. And in the other case, I get x equal. Now, keeping in mind that these are eventually being used to create angle measures. And angle measures, you have to be positive, right? So can we throw one of these out? Okay, why? Because if I substitute in negative 3 here, I'm going to get a negative 50. Right? So I know I can throw that out. So I have found x. X equals 8. So I could write this angle measure to be 40 degrees. I can write this angle measure to be what? 24 degrees. I can write, well, I would have to do this, right? 8 squared, 64 minus 24 would give me what? For kicks. Do we agree? Well, of course, because 40 plus, well, I won't say, it has to be this, right? We knew that. And then all I have left to do is find the measure of angle B. So to find the measure of angle B, what do I do? In this triangle here, so 24 degrees plus 40 degrees, subtracted from 180 is going to give me what? 116 degrees. And again, I could check that by adding it to 124 to make sure I get what? 180. Any questions? Now the theorem, this is the parallelogram diagonals theorem. And what this theorem says is that the diagonals of a parallelogram bisect each other. Now, I could easily see this again here, because if I were to fold, I would see that the length of these two pieces are congruent, right? And I would see that these two, I don't know if you can really see that, are congruent. So, I mean, I like to see on the paper. So let's state the pairs, right, that are congruent. I have BE is congruent to what? ED. And I also have AE is congruent to EC. So each of these, oops, is congruent, and each of these is congruent. Now, let's say that AC is 12x. This whole thing is 12x. And let's say that CE, so this whole thing is 12x. This little piece here, CE, is 7x minus 3. What is the relationship between this line segment and the whole thing? This is half of it, right? So this whole thing is twice this, or this is half of that. Means the same thing. So if I'm trying to find x, I can just set up a beautiful little equation. I can say 2 times this, or you can set it up using the half, it doesn't matter. 2 times CE equals AC. Isn't that true? Okay, so 2 times CE is 7x minus 3. Equals AC, which is 12x. So what do I have to do on the left-hand side of the equation? I have to distribute. And what would that give me? Equals 12x. Now I'm solving for x, so what would you do next? Okay, because we want our x's on one side of the equation, which gives me -6 equals what? Okay, last step to solve for x. Divide by -2. So that implies that x equals 3. We good? Now, in the next example, you have a parallelogram, then they give you the vertices. Now, do you have to draw it? No. I like to draw everything, so I'm going to go ahead and draw it. So I have a parallelogram, and it is P, Q, R, and S. So P is the point 0, 0, if I were graphing this on the Cartesian plane, right, the XY coordinate system, because these are little points, X and Y. Q is 1, 4. R is 7, 4. and S is 6, 0. And that makes sense. What I need to verify is that the diagonals bisect each other. So if they bisect each other, they have the same midpoint. So we need to review the midpoint formula. So I'm going to go ahead and draw my diagonals. That's one diagonal. That's another diagonal. And so this is the midpoint for each, right? It's the midpoint of this one. It's the midpoint of that one. So let's review the midpoint formula if we have forgotten it. X1 plus X2 divided by 2, Y1 plus Y2 divided by 2. So if I'm looking for the midpoint of PR, that line segment, that is going to be 0 plus 7 divided by 2 for the X value, and then 0 plus 4 divided by 2 for the Y value. Do you see how I just used these 2 points to substitute into the midpoint formula? Okay, so what is that going to give me in simplified form? 7/2 and 2. Now I'm verifying that it is the same point as the midpoint of QS. So again, I'm going to substitute into the midpoint formula. 1 plus 6 divided by 2 and 4 plus 0 divided by 2, which gives me 7/2 and 2 again. And since these 2 points are the same, we have shown that the midpoints of the 2 line segments are the same. Do we know what time we get out of this? Okay. We have 2 proofs to do. I'll walk you through the first one, and then you're going to try the second one on your own. We good? Okay.
Sorry, one second.
So in the next example, you are given 3 parallelograms embedded in one image, and you have to prove something. The 2 angles are congruent.
Wait, what's the number? Midpoint formula for PR. What's that number? It's like
0 plus 7 divided by 2, and then 0 plus 4. 0 plus 7, and then 0 plus 4. Okay. So you have been given 3 parallelograms. A, B, C, D, the big one. E, B, G, F, a little one. H, J, K, D, another little one. These are all little parallelograms. We are trying to prove that angle 2 is congruent to angle 3. That's what we're trying to prove. Now, some people put all the givens at the beginning, and some people spread them out where they need them. Since they're giving you the number of steps, I know how they've done it. So I'm going to tell you that they've separated it. It doesn't matter. But if they give you the number, you could have done this in 5 steps if you had put all the givens together. So I'm going to start with parallelogram A, B, C, D. That is given. I've been given that parallelogram. Now, since I'm looking at this big one, I can use a theorem, and I can look at 2 particular angles that I know are congruent. What are the 2 angles? So angle 1 is congruent to angle 4, because if the parallelogram, I'm going to abbreviate, if it's a parallelogram, then the opposite angles are congruent. Opposite angle theorem, right, for parallelograms. Now, I've also been given a parallelogram EBGF. So EBGF, so I can use the same property to say what two angles are congruent. Angle 1 is congruent to angle 2 by the same reasoning as above. And I'm abbreviating. Then I have a third parallelogram that has been given to me. So now I'm looking at this, so what can we say within here? Angle 4 is congruent to angle 3. Again, same property. So, what can I say? If that's congruent to this, and this is congruent to this, and this is congruent to this, by what property do I know? Yes, good. Try the next one. Try the next one. And based on the number of steps they've given you in the 2-column proof, separate the givens. Separate the givens. Because you have 2 things given. So go ahead, try that, and then we'll go over it. Did we get it? No. No. We're still thinking? Okay, I don't want to rush anybody, but it looks like we have some confused little faces. Okay, you have been given this parallelogram, SAIN. Now, we know within a parallelogram, the opposite sides are parallel. We also know that the opposite sides are congruent. And we also know about the opposite angles being congruent, right? So maybe let's use that fact. If ultimately I want to prove that these 2 line segments are the same and I see angles I see triangles. I see congruent triangles, perhaps, that I want to prove so that I can look at the corresponding parts. So I'm going to go ahead and use the fact that this is a parallelogram to say that AS is congruent to IN, right? Can we say that? AS is congruent to IN. And I know that because of the opposite sides of the parallelogram are congruent, right? And I'm abbreviating in the interest of time. So since these two are congruent, I also know which two angles. S and I. So angle S is congruent to angle I, because opposite angles of the parallelogram are congruent. Okay, I don't know what they are, but I know they're congruent. Now, I've also been given the fact that angle 1 is congruent to angle 2. So what can I say? The two triangles, so triangle AOS is congruent to what? NLI by what? Angle side angle, right? And since these two are congruent, what do I know? I have proven that AO and LN by what justification? That's right. Okay. Now, did y'all get the homework packets for the homework last semester? No? Okay. So the homework is listed on the calendar, right? It's also listed on Canvas, calendar. It's in your book. It's the same thing that you've been doing. You have problems. And here is the sheet that you're going to be doing them on. So as you do, this is for the whole unit. So as you're working the homework, when it comes time for that one to be due, you're going to scan it using OneDrive and upload it to Canvas as a single PDF, right? It's still the completion for 4 points, then the solutions will be posted. You'll self-check and resubmit for that extra point, right? So there's the homework packet. It makes it easier because you can give all the information so you know if it's longer, it's longer. Any questions?
So we just have to submit this with our answers and all our actual ones.
Yeah, you do it on here.
Okay. Oh, okay.
Yeah. Okay, and then if there's a diagram, you do the diagram, you know, whatever. But it tells you what we're looking for.
Mm-hmm.
So that way when you check it, the answer to you is the same.
Yeah.
Okay? How was class?
Good.
Any constructive criticism?
Is there a way to zoom in on that?
Yes. Yes. Absolutely. So like, let's take a peek. Is that zooming? There we go. All right, zoom in. Remind me. Right? Okay, so as we're doing that, can I see zoom? Zoom. Anything else? You don't have to tell me now. If you think about it, you go home, you send me a message, anything to help you.
Maybe go a little slower.
A little slower,
Just a little bit towards the end. It was a little fast.
a little fast with the, okay, absolutely. Just slow me down. I get excited. I get excited to do these proofs. All right, you have 10 minutes. You can kind of assess the homework. Maybe start looking at the homework in the book. 10 minutes. I know it's Friday. Kind of to see what lies ahead, right? Because I don't want you to go off. I'm here in tutorials, but I do teach 5 classes, so there's a lot of people that might be in here. But I'm happy to help you. Okay? Anybody online have a question? No? Okay. Y'all have a wonderful week, and you do not have to stay on the call.
Thank you.
Yeah. Welcome.
Thank you.
Yes, you're welcome. Yes. Hang on, want to stop recording? Okay.
I'd like the top.
Yes, sir.